Hi, this is Group 9 for EE533. Today I'm going to introduce our final project. Let's start with a video.
Imagine a narrow bridge over a rushing river, one so slim that only a single person can cross at a time. It's the only path forward, and many people are waiting to use it. One day, an old woman steps onto the bridge. She's moving extremely slowly, and out of courtesy, everyone else waits behind her. After long and long and long and long and long time waiting, at the time she reaches the other side, people realize she wasn't an elderly woman at all, just a mischievous kid pretending to be one, deliberately slowing everyone down and causing a traffic jam. Now imagine there's a smart traffic officer at the bridge. Instead of letting everyone through blindly, the officer observes how people behave. If someone looks suspiciously slow or unnatural, they pause and investigate before letting them pass. That's our LDDOS detection. Then, to keep things moving smoothly, the officer lets faster pedestrians cross first, or even sends a boat to speed up the process. That's our QoS dynamic scheduling. In short, we don't blindly block slow users. We identify who's truly in need, who's just pretending, and adjust priorities so that the system remains fast, fair, and efficient.
So that's the
Imagine a narrow
basic introduce of our project, which is a firewall solution based on OLD DOS detection and QoS management. So the stealth attacks that breaks the critical system in our daily lives. For example, slow loading creeping websites, API gateway silently suffocating, and game servers losing players by the trickery. So each of them would cause serious problems for their owners and the servers. And the main point that not like the DDoS, the LDDoS is a low rate type of a DDoS, which they are acting like the slow bandwidth connections, which would hardly be detected, which is for the normal systems who just like trying to defend the DDoS attacks, they cannot efficiently notice the LDDoS attacks. So what they're going to do? They are going to just like blindly ban all low bandwidth connections, kill the process of those slow speed connections. But that would also make the problem happens. As we all know, the videos chat is the best way to connect the kids with their grandparents. But because some elders don't know how to get better equipment, they might have bad Wi-Fi in their house. So which would cause the serious lagging and low speed connection between the customers and the server. So if the server just ban the slow rate connection between the server and the client to defend from the LDDoS attack, they are going to mistakenly kill the connection of the normal users. For grandparents, even though the lagging is serious, the Wi-Fi speed is slow, but they just want to hear the voice from their grandsons and saw the image of their face in some real time. So which we want, because of the blindly ban method algorithm to defend the LDDoS, this normal connection will be killed. We want to avoid this mistake happens. So we want to keep this normal connection as possible as we can. So how do we do that? The solution is that, first of all, in our systems, we have our algorithm to identify the LDDoS and check the IP address of that packet. Not only just like check the patterns, but also check the IP address. So if the IP address be shown in our firewall system's defense, we could just directly drop it. And then let the normal connection keep going. However, like we just said before, the LDDoS might acting like they are slow speed connections, like the normal users with slow Wi-Fi. So sometimes if the IP address not be shown in our firewalls, if we just see the patterns acting like the low bandwidth, low rate DDoS attacks, we might just leave it away, not just kill it, but just use our Q as dynamic justice to let the faster connection, the other packets go first. And when we are not busy anymore, we can then come back to handle the packet, the low speed packets, which might be the LDDoS attack. And in that case, when the normal connection are protected and the systems also stay healthy and responsive. So then let's move to the market part. The growth for the trend of the DDoS protections and the network processor market segment and the network security is growing really huge from the 2024 to the future. Also, for the global DDoS protection and the mitigation market is also growing. But all of them are just only defending the DDoS. Because LDDoS is really hard to detect. With such huge amount of the market of the DDoS, the LDDoS also have the positions. The LDDoS defense system also has the positions. As our competitors, the Red World Defense Pro, AWS Shield, and F5 Silverline, they both the cost per year is really huge. But because we're a hardware accelerator with FPGA, with simple hardware accelerator, we are much less cost. And because our target users are the small business, so if we check the DDoS incidents in DDoS per years for those small business, their experience larger than one DDoS. 62% of them are experienced larger than one DDoS attacks per years, and 38% of them have no DDoS, but that's more likely they didn't detect they didn't find that it's a DDoS attack. And 53% of them also find that they might do not have LDDoS, but as we said, it's just hard to be detected. And even though it be detected, the 37% of them experience larger than one LDDoS attack per year. So that's our positions. So for our target users, because they are being impacted by those attacks, so the revenue loss of them is that 50% of the small business lose the larger than $20,000 per attack. And the downtime cost that is averagely just $5,000 per hour for a 50-employee companies that being attacked by the LDDoS attacks, which be shown in the S&P Cybersecurity Report in 2024. So why choose us? Because for our systems, we have unique LDDoS detection using the power spectral diagram with network processor, and the hardware accelerated real-time scheduling make it have low latency, and the QS module integration makes the user experience be maintained.
Hello, this is Haoran Fan from E533 Group 9. This is our demo video for our final project. Okay, let's get started. In our final project, we want to build a system generated with our pipeline processor, the firewall, and QoS system to decide to drop the packet or not and generate the output sequence for all the packets. From the input to the output so that we can set some priority to send or and deliver all these packets to the next level. Okay, so this is our general idea for our final project. Okay, so as you can see, we will have four parts for our final project, and we will have a pipeline processor, which we would like to initialize assign initialization data in our system. And for example, we could initialize and input the data to the data memory, and then we will use this pipeline processor to load all the initial data to from the data memory to the register, and then we will use the final estimation to control the pipeline processor to store all the initial data to our firewall part and QoS part, like the drop IP that we want our firewall to drop, or the assign IP for different queue in our QoS system, and with value for set up our different queues priority. So this is our general idea for our final project. Okay, let's get a closer look for the firewall and QoS part. So in our firewall, we would have a drop IP register to store all the IPs that we want to drop if the packet is from this source IP. So for example, we would have in our test bench, we would use pseudo package, like for example, for the packet one, we want to the packet one begin with one, and the packet because we define our packet header in this format, like uh the first 32 bits is this field, and we define this 32 bit as packet begin 32. So packet begin at with 3, we will get the source IP from for this packet. So we could detect the packet source IP in this way. So, for example, if we detect the pseudo packet, which in our test bench packet one begin with one and one add with 3 would be 4. So the packet one source IP would be 4. So if we initialize the drop IP, like we would drop the packet which has source IP for packet 1, 2, 3, or 4. So for the packet one, we will drop it because the source IP will be 4. Then following this way, we could build our pseudo packet in this way. So for example, begin with 2, so we mean it means that this is packet 2. So the source IP will be 8 because 2 the first 32 bits in packet 1 will be 2 and add with 3, so the source IP will be 8. So for the source IP which has source IP 8, that um it will match with our defined source IP in Q0. So this packet 2 will be stored in our Q0. Uh, Yeah, so it will be stored in this queue, and similarly for all the following packets that we would also build in this way, so we can decide which packet we would like to be dropped and which packet will be stored in different queues. So in our design, we would like to detect the LD DOS attacked We would generate with our LD-DOS detection. So because it is unpredictable and uh, attacked our machine in some genre sequence. So firstly, we don't know that if this packet is LD-DOS attack. So we will store in this Q0, which we will build like uh for the Q0 we want to announce this is for suspicious packets. So if we don't know that if this packet is from a lower bandwidth user or the LD-DOS attack, so we would put this packet to our Q0. So in our QS part, we will announce this Q0 as Q suspicious. Yeah, so for Q0, we will announce Q suspicious that if the packet source IP didn't match with our packet 3201, then uh, we will store this packet to our Q0. And uh, this is and by assign for different width value for different queue with different depths. For example, if the packet one's depth has if the Q3 has stored, for example, like three packet, then for our for Q3 that we would assign for the weight value for different queues with different depths. So for example, if Q3 has the depth 3, so the weight value will be 29. Then we could compare for different queues weight value to decide which packet would be came out first for different queues from different queues. So this is our general idea for our firewall and QS part. So by following with this initialization data, that we could store the initial assigned data in our firewall with QS part system. So for example, we could assign our drop IP and different define source IP to store in different queues. So this is our firewall's QoS part. So go to the top level for our system that we will use pipeline processor to initialize all the initial data into our firewall and QoS system. So for example, we would like use this pipeline processor to initial the drop IPs into the firewall and assign IPs in different queues for QoS system and the weight value into the QoS system for different queue steps. So next, we will build a pipeline processor to load the initial data from the data memory for the pipeline processor and store them into our firewall and QoS part. So this is our definition for our pipeline processor's data memory. For example, we build our data memory in the workaround type structure, and we would assign different address to store the specific data. For example, we would assign our data memories address 0 to store the Q0's assigned IP 0. So in this case, following with this definition, we will decide where to store the initial data. For example, in this test bench that we want our firewall and QoS system to working properly. So for example, For the source IP, define source IP to store in Q0, we could assign our assign IP in the address 0, 1, 2, and 3 in our data memory, and we could also assign our firewall drop IP in the assigned address in our data memory. So following with this this table, then we could build our data memories initialization file. So this is our data memories factor file to store uh into our data memory. So for example, we could this is for um the address 0 in our data memory, so we can check that we initial the 5 in our address 0. So this is for Q0's assigned IP, which matches our test bench in our firewall QS part. So we would like to store the drop IP following with define source IP in Q0, defined with 5, 6, 7, and 8. So we will initial the factor file in our data memory like 5, 6, 7, and 8. So following with this structure, we can initial the data memory in this type. So next part, we will build our pipeline processor uh, in the multi-thread type. So for example, in our design, we will have 4 queues, and our firewall could also store for drop IP. And for different queues, it will also have the weight value for different depths. So we can definitely build a full thread pipeline processor. So this is for the instruction memory in our different thread. So for example, we assign different data memories in different address in our data memory, and we would also define the assign store register file the to different threads register file. So for example, we would like to load the Q0 session IP in our thread zeros address 22. So following with this definition, we could build our instruction memory in different thread. So for example, we will load the data memories address 0 to our thread zeros on register 22. So this is our instruction definition in all the 4 threads. So then we would also define a new type of instruction, which we would name it like initial. So for this initial instruction, it's like to after we load all the initial data from our data memory, then we would load them into our local register for different thread. And after we load all the instruction, we would initial them into our firewall and QS part. So we build this new type of instruction, which we named as initial. So for this initial, we would assign different a new type of operation code, and we could uh, decode it and to build the control signals for this new type of instruction in our control unit, in our pipeline processor. So we could initial for build initial instruction for all different thread, and after that after we operating the initial instruction, that means our pipeline processors has done for its initialization work for our firewall and QS. So next part is to test this following with this definition and design. We would like to test and simulate our final project's workflow. So next part, we would like to do the simulation part. So as I showed before, we would initialize our data memory and the instruction memory in our block run in our pipeline part. So for example, this is data memory, factor file, and for the instruction memories factor file, we will also initialize initialize our instruction into our instruction memory, and we build this we generate this instruction into machine code so that we build this instruction memories vector file. So this is the initial file for data memory and instruction memory following with this definition. So next part, we would like to simulate for the final project. And yeah. So in our final project, we would have all this for part of components in our final project. So from the Verilog file, we can see this first part with firewall is QS, and then the final estimation to control the state for the whole instruction, for the whole system, to like the initial state to for the pipeline to load all these initial data into the register in different threads, and then after we operate the initial instruction, that we could load all the initial data into firewall and QoS system. So after that, this is the first stage in our pipeline process, in our final project, and then we would the next state would be firewall in. So which means that the firewall could receive the packet, and then the next part would be firewall out and QoS in, which means the firewall could output and to decide to drop it or deliver it to the QoS system. So for the final state would be the QoS out, which means QoS could be reordered or the package that we received from the firewall and then reorder them with some priority and then output to the next part. So this is our final submission, and then we'll yeah, so this is a firewall part and finance submission part and pipeline processor part. So, oh, by the way, we will also have some to FIFO to store the packet in and packet out so that we can simulate uh them. So we will build packet in to store the packets that we would receive to the firewall, and then the packet out to store the packets that output from the QoS system. So we will also have to FIFO part. And for each FIFO, we can see it has 34 bitwise, because we would also in our system we would want to know which 32 bit is a packet begin and which 32 bit is a packet end. So in our firewall's QoS part test bench, we can see for the packet one that if we input the first 32 bits, we would also enable the packet begin bit, which indicates that this 32 bit is the first 32 bit in our packet. And for the last 32 bits, which is 6, then we will enable the packet end bit, which indicate that this 32 bit is the end of this packet. So uh, add all this up, then we will have 32 bitwise packet bit, and we will have 2 bits for indicate the packet begin or the packet end. So totally we will have 32 bit. So for our final project for the packaging and packet out FIFO, we would have 34 bitwise. So this is the packet in FIFO and packet out FIFO. And yeah, that's it. We would like to simulation for our final project. And because we want to build a database for the final project, so we would have this kind of input port and output port. So for the data memories, writing port and writing address port and writing enable port, we could change the initial data in our to stored in our data memory and finally load to the firewall and QA system. So this is a simulation for our final project part. So um yeah, this is a bit set output from the package in FIFO. So we can see we would have packet begin and oh sorry. This 34-bit is packet output from the packet FIFO packet in FIFO. So we can see from this bit the packet in FIFO would be enabled to output. So the first bit will be most significant bit in our 34-bit wise will be the packet in and generated with our data bit, which is 1. So this bit means this is a packet begin and the data bit will be 1. So this is a output from our packaging FIFO. And next part, this is the output from our pipeline processor part. So in our pipeline processor, we would have like pipeline. Yeah, we will have output to connect it with our firewall and QS part. After we load the register from the data memory to the register file, then we would use the new kind of instruction initial to store all this data into our firewall and QS. So we would have these kinds of package this kind of output port connected with our firewall and QoS part. So, for example, we would connect the output to our firewall QoS input port. So, um, the the first uh the first sound signals will be the load register start, and then we can see the assigned IP for different queues will be changed because we finished the load to the local register file, and we can see in the first clock we would load 5 for assigned 0, and then we will load 6, and we load 7, and finally we would load 8. So similarly with the different thread 0, thread 1, thread 2, and thread 3, we can load for different data and store them in their assigned register file. So this is the load part, and this is the load wait value. Oh, and this is for load the drop IP, I mean, so we will drop the IP like the packet one, IP one, two, three, and four in our sudo package. So this is a drop IP load process. So finally, we would load the wave value to initial the yeah. Firstly, we will load load a SAN IP for different queues. Then we will load the drop IP, and finally we would load the wave value for different queue. So from the output for the pipeline processor, we can see this program is working following with our design in our sequence for the instruction in our in different thread. So first we load the assign IP, then we load the drop IP, then we load the wait value. So after we load all this data, then we would write into our firewall and QS part. And after that, the final submission would be uh, will move to the next state, which is a FIFO writing state. So in this state, the firewall could be is initial successfully and could be writing and receive packet. So from the waveform, we can see the our packet in FIFO will be output enabled, and all these packets from the packet in FIFO will be output, which means the packet will be output from the packaging FIFO and be inputted to our into our firewall. Um, yes, this is all for our firewall writing state. And after that, our packaging FIFO would be empty, and then the packet out is indicate that this is the output for our QS part. So for these three bits, we can see the output sequence for different packets. That the first output packet will be packet 3 because in our test bench, our packet 3 will be stored in Q0, I think. Q1. So will be output first because packet 1 will be job, and packet 2 will be Q0, and packet 3 will be Q1. Because Q1 has higher priority than Q0, so packet 3 will be output first. So from the simulation, we can see the first output packet from the QS part is packet 3. And then here's the begin packet 3 and the end packet 3. Then following with packet 6 and packet 30, and then packet 7, packet 2, and packet 10, and following with that. We can check if the firewall dropped the packet successfully. So let's check for the output port for our firewall part. So in our design, we would like to drop the packet set which has a source IP with um 1, 2, 3, and 4. So by checking these three output ports, we can check if the firewall outputs this packet that has this assigned drop IP source IP. So we can see for our firewall, this is the first packet, that we didn't output it because we can check uh, we can check the dropout output port to see that if the firewall decide to drop it or not. So yeah, we can see for the packet one, we decide to drop it. So we will disable the firewall auto enable, which means we didn't allow the QoS part to store the packet one. That means the QoS part will be disabled to writing for the packet one. And then for the packet two, we will enable it to write into our QoS part, which means we didn't drop our packet two. And then for the packet three, we didn't drop the packet three and some following with this. So by checking the packet dropout and firewall out enable, we can see which packets that the firewall will decide to drop and which packet not. So this is our firewall part. We can see the firewall working successfully, and then the QoS part that is for this bit. So we can see the QoS part for sample will be packet 3 and then packet 6, following with packet 7 and packet 2, packet 10, 11, 8, 13, and 9, which we reorder the packets sequence and put some priority to store in different queues. So we can check sets RP auto enable pin to see that which queues is output enable. Is for QoS output. So we can see we decide to output Q1, the packet in our Q1 and also Q1, and after we output three packet in our Q1, then we will decide to output Q0 and then output Q2, Q3, and Q1. So by checking the read pointer in our QoS part, we can check which queues decide to output first, and then so finally, all this output packet from the QoS part will be stored in our packet out FIFO. So finally, let's check for the packet out FIFO data in. Yeah, this is a packet out FIFO data in, which also has 34 bit. That the first bit indicates is packet begin and then packet end. So we can compare the packet of FIFO with the packet of from the QoS that we can see all the packet will be imported into our packet of FIFO and stored into it. So this is a writing port, and we can check from the readout port that we would like to read out the just 0. Then we could read out the data out with this um with this 34 bit. So the first data out which has stored in our address 0 in our packet of FIFO will be the packet begin for the most significant bit, and we can check the data bit which has 110 and all zeros, which means the first data bit will be 3, which is packet 3 output from our QS part. So from the simulation result, we can see our system is working properly as we designed. So this is the simulation part for the final project. But when we generate our bit files, we can see the this is a final project, the total final project part, which we will have our pipeline processor and the firewall part, QS part. And after we generate this, we find out that this is a mapping report file, which we would overuse our slice on our native FPGA. So finally, we decide to uh, not use this pipeline processor part. We would only use the firewall part and QS part that we could uh, input all this initial data manually into our system. So we generate a new project which we call the firewall QS project that we would only include the firewall part and the QS part. And we will also generate our packaging FIFO and packet of FIFO. So let's check for the simulation for the firewall and QS part, which is this one, which we would manually input our assign IP, draw IP, and wait value for this part. Yeah, for our firewall, only we include the firewall and QS parts in our project. We would manually input the assign IP, the drop IP, and wait value into our system. So all this port is input port in our firewall QS part. So yeah, we would manually input all this data into our system. And by checking the packet of FIFO import, we can see the output sequence is exactly like we design our total generated with pipeline processor part. So the project that only with firewall and QS would also working correctly as we design. So we could control it by the initial uh initial control signals. So for example, in the if we enable it, that means the system will be start working. Then after some clock, if we disable it, then all the packets will be cleared. And after 6 o'clock, we enable it, then the system will be reset and again working as we designed. So this is our final project, which we only generate with our firewall and QS part. So after that, we build the we build a bit file, and from where's the map report? Yeah, from the map report that we uh decrease our use for the slides, and this time we generate our bit file successfully, and there's no errors in our during our building and compile process. So finally we generate our bit file. Then we would upload it into our NetFPGA. And next part, it will be demo our NetFPGA output result part. Okay, thanks for watching.
So I'm Yiyu. Now we're going through the software of our control panel. It's written by Python with GUI enabled. First, on the top is our standard GUI library, ticker and TTK for widget plus message box for dialogues. We need time and collection for the buffering traffic data. Matplotlib for our live graph and threading plus Q for non-blocking SSH calls. Paramiko handles our SSH and NumPy, and C is used in the attack detection mask. And this is a list of our software and hardware register of our NetFPGA, and you check the defines here is the header file from NetFPGA. And for the SSH manager, it works with Paramiko to run register read and write asynchronously. In Connect, we start a daemon thread calling the loop, and the loop post command of command queue, execute them, and push the result onto the response queue. And read read, and this read read will place a read request and wait for the response. And because our control panel is connected to our NetFPGA, so via SSH, so it can put the data from NetFPGA in real time. And this is connect, and this is for the functions regarding SSH. And then for the firewall part, this is our holds our rule sets and QoS policy plus DDoS and LDDoS detections. And re-register the delegate to SSH manager and allow and block updating memory rule sets, and add QoS rule appends IP or port-based QoS rules. And this register, and we can allow port, block port, allow IP, block IP, and add QoS rules, and we can get the priority of the packet, and we can look up for the priority and filtering. And for our traffic monitor part, the traffic monitor runs its own thread, polling from netfj every second, and it callbacks to update the UI graph to notify the app on attack detection events. And the firewall app part, in the main app constructor, we initiate the SSH manager firewall and the 50 entry DQ for traffic, and we wire up traffic monitor with UI callbacks, and we call setup method for style UI tabs and the graph showing on the main screen, and we can launch the SSH connect routine on a background thread. And this is for that part. And this is just to match and set the band IP or something like that. And for our another feature is we embedded a matplot figure into our control panel, so then use function animation to redraw every second traffic counter to should drive from both graph and rolling DDoS and LDDoS detection. And finally, this is the main function. It will launches the Zeekr and make the program runs. Okay, then we are going to looking about the actual demo of our control panel. Okay, now let's go. We're going to the actual demonstration part. First, let me talk about let me talk about our test scripts. And firstly, we're taking the SSH connection to one of the nodes, which is this, and this is the username, this is the password, and we are just flooding this one of node, which is this one, and target IP with this on this port and flood it with this algorithm. And this is for connect to the SSH, and it's connecting, and we're going to test it the DDoS, and this is for LDDoS, which is low rate DDoS, and we're protecting this IP, and we're SSH to one whole node and send to this IP, and we are going to perform the low rate DDoS by using this algorithm. And let's take a test. First, we can open our test panel, control panel. That's very control. Yes, unable to connect that picture. Oh, that's because I forgot to turn on my VPN. One moment. Sorry. Now the VPN is successfully established. Let's try again. Control panel. Now it's showing successfully connect to the NetFPGA. So our panel is attached to the NetFPGA. Let's run the DDoS test. .py. Yes, DDoS.py. Let's run it. Now it's flooding the node we desire. Now it's showing that DDoS is detected by our backend NetFPGA, and because we're targeting the small business, so the user can simply just click apply, and that IP is banned, and it's showing that it's unable to send to that one because it's banned. Now let's turn it off, and we are now allowing this IP deleted from our firewall, and we can perform the LDDoS test. LDDoS.py. Let's run it. So attacking. Now the low-rate DDoS is detected by our backend server, by our NetFPGA and software. Now we can change it. Let's try change it the QS priority to medium and click apply. Medium and apply. Now see the medium is the color, and the medium packet is shown on the graph that around that packet, and it shows prioritized as